All right. Hi, everyone. This is Dan Barry, and I'm at the NOAA Climate Program Office. And I want to thank everyone for joining today for this webinar on fire modeling and prediction. This is the second part of this two-part short webinar series on the topic of fire modeling and prediction. And we had another webinar last Thursday where we covered a number of topics, including interactions between fire and weather, efforts to better simulate fire in global models, and evaluations of the causes of extreme fires. In today's webinar, we're going to hear about a number of complementary topics, including seasonal, short-term, and decadal fire prediction efforts, regional fire modeling efforts, and better understanding of fire regimes. And we're really lucky to have another 4 fantastic speakers today. I'm really excited about this group. We're going to hear from Ed Delgado, who's at the Bureau of Land Management, Uma Bhatt, who's at the University of Alaska at Fairbanks, Jim Randerson, who's at the University of California at Irvine, and Adam Kochansky, who is at the University of Utah. And as with last week, I want to thank you, Emily, for all your work to help set this up. It definitely took a lot to plan these couple of webinars, getting these 8 speakers to come to a common time. And I want to thank the speakers as well. We definitely had a lot of iterations by email, and hope that we didn't drive all of you completely crazy. I'm happy you all decided to show up today in spite of our massive amount of communication. So I really appreciate all of the effort all around to get this webinar together. So we're going to start with Ed, and let me see if Ed's on the line. Ed, are you there?
I am.
Okay, great. So Ed, I'm transferring control over to your computer, just like we did before. Great. All right, we can see your screen, so whenever you're ready, please go ahead.
Okay, great. Good morning, good afternoon, wherever you are, and I'm happy to be on this call. Some of you that might have attended the Columbia University Fire Prediction Workshop last fall may remember some of my slides, so hopefully I won't bore you to death. But I wanted to talk a little bit about the challenges facing wildland fire forecasters, but before I do that, I just want to introduce myself, Ed Delgado. I'm the Predictive Services Program Manager here at NIFC in Boise, Idaho, the National Interagency Fire Center. And I wanted to give just a really quick background of what we do in Predictive Services. We were established in 2001 as decision support for fire management and resource distribution. We have 23 meteorologists scattered around across 11 offices, and you can see where our regional offices are, geographic area coordination centers. They each have 2 or 3 meteorologists that basically forecast fire weather and fire danger conditions across those areas, and then we kind of aggregate everything into a national forecast. We also have 3 fire analysts that work at a couple of the geographic areas, and 1 here who provide a little bit more expertise in fire behavior and fire danger for the meteorologists to complement the meteorologists. And our primary role is to support the strategic planning and operational management of wildland firefighting resources, and the 3 key functional areas that we work in. Obviously, fire, weather, and climate is very important. We deal with fuels and fire danger, how the weather and climate affect those things, and then we also look at fire activity and resources intelligence, where the fires are, what kind of resources are being committed, what management strategies are being used, and all of those things combine to help us refine our predictions as we move through the day and the season. And so that's what I want to get into, is as we try to combine all of those things, there are a lot of challenges that we face with regard to predicting for fire. It's hard enough that we're trying to predict the weather, but now we're trying to predict the impacts of that weather on something else that's very difficult to forecast. So among the challenges, we really have to define what it is we're trying to forecast. We could try to forecast number of fires. We could try to forecast the number of acres that are going to get burned. We could try to forecast a number of characteristics about fires themselves, but each of those comes with its own with its own issues. For example, trying to forecast the number of fires. We can forecast lightning fairly well and maybe determine what the probability of an ignition is from from lightning, but then we have to deal with the unknown element, the human element, and when those fires, where and when those fires are going to start. So that's obviously a challenge for us. We also have to understand what the business needs are of the fire organization. You know, obviously, first and foremost, their obligation, their business need is to try to put fires out, and they need to know where those fires are and how they're going to act. But there's a lot more to it than that. There's identifying threats to humans and property, so values at risk, you know, what the cost benefit is of trying to put this fire out versus another fire. And so we have to balance that in our assessment of the fire prediction problem as well. And then, of course, we deal with all kinds of spatial and temporal scales, and I'm glad the speakers following me will address some of those, some of the breakthroughs in that kind of prediction. But spatial and temporal scales, we cover the entire United States, and this is just the fire perimeters last year in the western United States, so you can see it spans the entire west from the Mexican border all the way to the Canadian border, and from the west coast all the way to the front range of the Rockies. And that doesn't include the fires in the eastern United States, where in terms of numbers we have many, many more fires in the east than we do in the west. They just don't generally reach the sizes that we see out west, but they're no less important to our forecasting program and to our fire management program. So those are the three big challenges that we have to face at all the scales that we're forecasting for. So I talked about what are we forecasting. Well, like I said, we could talk about ignitions. Do we want to try to forecast the number of fires we're going to get? Well, that comes with its challenges, and there may be the value of forecasting the number of fires changes depending on your location. Like I said, we have a lot more fires back east than we do in the west. They're just not as big and oftentimes not as significant as they are out in the west. So is that a valuable predictor for us? Probability. We can try to forecast the probability of ignitions, and like I said, we do pretty well with lightning-started fires because we have a good understanding of lightning, when we're going to see lightning, and the probability that lightning is going to cause fires given certain conditions, environmental conditions such as fuel dryness and things like that. But it's not the only source of ignitions for us. We have human-caused fires, and when we talk about human-caused fires, we're not just talking about someone going out and throwing a match on dry grass. We're talking about things like power lines arcing or sparks from trains out in the interior deserts of the West, or you know, a car out in a hot catalytic converter, or anything that's related to some anthropogenic activity. And those are very difficult to predict. Obviously, we can't predict how people are going to interact with the environment, and we also can't predict how things like power lines are going to arc or trains are going to spark in the grasses of the desert. So probability is difficult, and of course that relates to cause. Is it human caused, is it lightning caused, or other factors might be involved, or a combination of the two. And those are things that we just don't have any skill at predicting. So that brings up a challenge for us just in and of itself. Of course, size and growth, or thresholds, size thresholds and growth are important. So looking at this little chart, you can see just the range of fires that we had on this particular day in Montana, in the Pacific Northwest and the Northern Rockies, I should say. And so you can see we range from just a few hundred acres all the way up to tens of thousands of acres in this fire scale. So, and you can't really say that one fire is more important to the other based on how rapidly it grows. So, for example, a 10% increase on a 100-acre fire is a lot different than a 10% increase on a 40,000-acre fire. So if we're just trying to look at growth rates or certain specific thresholds, 10,000 acres out in the wilderness of Alaska may not be as important as 1,000-acre growth in Santa Barbara. So it's difficult to find those break points where size is a good measure for what we're trying to forecast. And then, of course, environmental conditions. We can just forecast the weather conditions that we know typically drive fires, like wind and temperature and humidity and instability, things like that. But we still have to understand how those things are going to affect the fires that are on the ground, as well as contribute to more ignitions in the near term. And that's going to affect how we distribute resources and how we manage the fires that we have and the ones that we expect to have in the coming days. So it's constantly, we're constantly sifting through all of this information and trying to make the best assessments on a day-by-day basis and even a season-by-season basis to help us determine what's going to be important in any given situation. And then the other thing is we have to establish what the business needs are. Obviously, in wildland fire management, there are many. So the first and foremost is safety, not just public safety, but the safety of firefighters. And this is becoming an even bigger problem as we start to understand that the impacts of smoke, not just on the public, but also on the firefighters. Firefighters spend a significant proportion of their day stuck in smoky conditions, and that accumulating effect of that exposure is creating, we're starting to realize there's a lot of long-term health effects on firefighters, and so that's an issue that the business has to deal with. Suppression, you know, for years and years in this country, we did full suppression where we put every single fire out as fast as we could until we realized that that was actually unhealthy for the forest, especially where fire is an important part of ecosystem health. So we have to balance the business need of suppressing the fires in the protection of life and property with keeping the ecosystem healthy. Of course, natural resource management is a big thing. You have, you know, obviously the timber industry, the value of the timber, and also just the tourism aspect. You know, people don't want to go to Yellowstone if it's completely burned down. So those kinds of things are important. And then, of course, firefighting resources management. We only have so many resources that we can put on fires, so we have to balance the resources that we have with all the other issues like suppression and safety and the conservation of natural resources. So business needs are all over the map as well, and those figure into the challenges that we have to deal with. And then, of course, spatial and temporal scales. I've talked about this already, but we have all the different scales from the local unit, the incident level, where are we seeing initial attack, when do we see ignitions and immediately put firefighting resources, all the way up to geographic area, more regional scales, and then, of course, national scales, which we start getting into spreading our resources really thin. And then, of course, international scales and global scales where we have to share resources. We have agreements with the Canadians and the Mexicans to share resources with them. And, of course, there are also, we're starting to see more international collaborations across the Atlantic Ocean between the United States, Canada, and Mexico with the Europeans in Spain and Portugal and along the Mediterranean and places where we're starting to see a lot more fire, a lot more significant fire, at least learning about it on this side of the Atlantic. And then, of course, temporal scales. We deal with burn periods, day by day. What's the fire going to do during the next 12 hours to what are fires going to do over the next several weeks, and how are we going to manage our ability to fight those fires, to seasonal. How do we prepare for the next fire season and make sure we have the right strategies in place, the right resources in place, and other considerations with how we're going to deal with the fire on a season-by-season basis. So all of these challenges raise a lot of questions, and right now some of the things that we're trying to do about them is we need to clearly define what it is that we're forecasting. You know, we have some fairly robust ways of doing forecasting. We can do straight weather forecasting. We understand the relationships of weather and the fuels. We understand somewhat how certain environmental conditions lead to more fire, but we need to understand more clearly what it is specifically that we're forecasting. Is it number of fires, rate of spread, days until the conditions will change enough that we can have a more noticeable impact on the fire itself. Those kinds of things. And also, we like to talk about normals in fire, and we really haven't clearly defined what those normals are. And those normals change across different parts of the country. And so firefighters kind of have an innate sense of what a normal fire season is, where they usually fight fire, but our firefighting resources are mobile and we move them around a lot. And so this normalization, we don't have a standard definition of what that is. So if you take a firefighter from Arizona and you put them on fires in the eastern United States, normal is a different thing there. So we have to be able to understand what that is and what it is we're forecasting and be very clear about that. And we also try to tie things to business needs, tactical and strategic decisions. How do we, what kinds of decisions are we going to make about how to manage fires, full suppression, or trying to use the fire as a natural resource to help manage the ecosystem and keep it healthy and use the fire to our advantage. And then, of course, that economics plays into that. How much money do we have to do this? Are we spending the money in the right places? Is putting a bunch of air tankers on a 50,000-acre fire a good way to spend that money, or will we be better off putting those air tankers on a fire where we know they'll actually have a more significant impact? For example, air tankers are really good at helping to keep fires small, but when they're really big, they don't really provide a lot of benefit in terms of putting the fire out. They become more of a protection of property kind of thing at that point. So we have to weigh the cost benefit of doing those kinds of things from an economic standpoint. Then, of course, we can just do plain old weather forecasting. We're pretty good at that. And as we keep doing that and we continue to identify the relationship between weather and fire, that good old weather forecasting skill is going to pay dividends in the long run. So we have to make a more concerted effort to improve our ability to forecast on all the scales that we deal with in fire, from day-to-day forecasting, mesoscale type forecasting, all the way out to seasonal and multi-year forecasting for the planning purposes of fire. So that's all I have. It's kind of a quick, kind of breeze through that pretty quickly, and hopefully you guys will have some questions.
Yeah, Ed, that was great. Really nice to look at, a lot of the multifaceted issues y'all are trying to balance. So if there are questions on the line, you can send me a chat message. Let me know you have a question. You can either type your question in or just say you have a question, and I can unmute you to ask. In the meantime, any questions in the room for Ed?
Yeah, hi Ed, this is Anarita Mariotti. Very nice talk. I wonder if you can elaborate on needs and activities that you may have on longer timescales, for example, to support planning or longer timescales than the seasonal.
Yeah, so seasonal forecasting, when we currently do a monthly outlook that goes out 4 months, and that helps us kind of get a big picture, helps our higher level leadership get a big picture of what they're going to engage in over the next few months. And it also helps with establishing these international relationships. For example, we do a lot of collaboration with Canadians, and our fire seasons line up during the summer. And so if they have a really bad season, we can provide them resources to help, and vice versa. But if we both have bad seasons at the same time, that sharing isn't there anymore, or it's much harder to accomplish. So that's where the seasonal forecasting, one of the areas where seasonal forecasting comes into play. But as we get beyond that, as we go into multi-year forecasting of fire, that becomes more a budgetary thing. Our budget cycle is 2 and 3 years in advance, so we're actually planning for the 2021 and 2022 fire seasons from a budgetary perspective right now. And that's kind of where the weak area is. We don't have a lot of skill at forecasting 2 and 3 years out for fire seasons. So those longer range predictions, the multi-year outlooks would be a great benefit if we can start improving the quality of those.
Thank you.
So Ed, Jim Randerson had a question for you. He is interested in whether we know what areas of the West can be forecast out to 7 days successfully, and what areas where the time horizon is significantly shorter than that.
Well, we currently have a product. It's called the 7-Day Significant Fire Potential, and we're in the process of improving that. But it's basically a probabilistic model based on historical fire occurrence and the correlation of some fire danger indices like energy release component and 100-hour fuel moistures, dead fuel moistures, and things like that. And we do pretty well with it. The problem with the model we have is it's primarily focusing on fuel dryness and how that correlates to fire activity, historical fire activity, and then we enhance it using meteorological triggers like lightning for ignitions or certain environmental conditions that might enhance fire activity, such as wind and humidity combinations, like we saw last week in the Great Plains with the strong winds, the low RH. When you got fires, they just took off. So that's kind of where we are right now in Predictive Services with our forecasting. And we do pretty well out to about 3 or 4 days with identifying kind of the general forecasting of fire. If we can identify some fairly significant events like major lightning outbreaks in July on the West Coast, we can usually go out to a week to 10 days to identify those potential significant events. But in terms of forecasting more precisely where fires are going to occur and when they're going to occur, we're not anywhere close to being able to do that yet.
Yeah, that's great. Thanks, Ed. I think that answered the question really nicely, and I think Jim's going to pick up on this a little bit in his talk as well. So I think in the interest of time, we should move along to the next speaker, but that was a really great introduction to the webinar and the topic, Ed, so thank you for that.
Great, thanks.
Okay, great. So the next speaker is Uma Bhatt from University of Alaska. And Uma, if you're on the line, I'm switching control over to your computer right now.
Okay. So can you see my slides?
Not yet. If you go in WebEx to the Quick Start tab and then click Share Screen, we'll be able to see your screen.
Got it.
Great.
So thank you. Well, I'm going to talk about seasonal forecast products for fire managers in Alaska. And I think Ed did a great job of really emphasizing how challenging this is. And really, our overall goal is to come up with seasonal products or use seasonal forecasts to make products that can be used for decision support several months before the fire season. And again, challenging. It's kind of the thing that keeps coming up. Wildland fire burns many acres in Alaska. This is a time series from 1940 until 2017 of acres burnt in millions, and fires are very costly. The 2004 fire cost over $35 million in property loss and over $17 million in emergency personnel. That was our kind of worst fire year that everybody in Alaska talks about. And more recently, we had the 2015 fire, which was also the second highest acreage burnt. And one of the things that has come out with talking to fire managers is if they had information a season in advance in March, that would be very helpful because that's when they're making decisions about allocating resources. Fires in Alaska start earlier than in the lower 48, so often since resources are shared, making those decisions intelligently, it would be helpful. So that's what motivated this work. And also as budgets shrink, this information is going to become more and more important, so it really motivates why this needs to be done for a variety of reasons. So our team, this is kind of a busy plot, but this is our team of interdisciplinary scientists, all the atmospheric scientists and climate people in the lower right. We work closely with the Weather Service in Alaska and Rick Toman, and Pei Tao Peng from CPC NCEP is also part of this team. And then we have the Alaska Fire Science Consortium, which is a boundary organization that links kind of, what we do as academic researchers with boots on the ground people in predictive services like Heidi Strader, Sharon Alden, and Gabriella Branson. And I think the discussions with these folks has really changed the way we would have done this research. So I think it's been very beneficial. So let me tell you a little bit about fires in Alaska. Basically, the season's a little bit different than in the lower 48, where the snowpack really matters. Here in Alaska, what's more important is when the snow melts. The snow doesn't really provide much water content, so it's really, if the snow goes early, then the ground starts drying immediately. And for example, in 2015, the snow went away early, and then there was a fairly long dry period. And the plot shows cumulative acres burnt in millions of acres, and it goes from early June to October. And these are fairly our extreme fire years, and they were all a little bit different. 2015 was of concern because we had lots of acreage burnt early on, but then because it was triggered by dry weather in May and June, and then in the middle of June, we had an incredible number of lightning strikes which flared up the burning, and a lot of the burning that occurred over a very short period. And then in mid-July, we typically start getting our rains, and once they start, if they're continuous, it puts out the fire season. In 2004, that rain didn't last. It was very short, and we ended up getting a lot of acres burnt later in the season. So again, the intra-seasonal weather variability ends up determining the weather burnt, the number of acres burnt. So there's real potential for using weather forecasts. And this is, at the bottom, I have a little, a side note that there's been some studies that have looked at the attribution of the 2015 fire season due to human activities, and one paper for Alaska as well as for the lower 48 suggests that yes. So again, we might be dealing with more of this in the future. So what we're using is we're using the Canadian forest fire indices, which were developed for the boreal forest, and we're focusing on this buildup index, which is an integrated index that provides potential fuel availability and flammability. And there are a variety of other indices are calculated, but this is the more integrated. The initial fire spread and the fire weather index are more important on the shorter time scale, but for the seasonal time scale, the buildup index is what we're focusing on predicting. The Department of Interior through the Alaska Climate Science Center has funded some work that hasn't begun yet on exploring other indices. There's been a variety of new work done and applied to the lower 48. So there's going to be some re-examination of, are there other things that we can use for Alaska and boreal forests. This is a typical table that a firefighter would use in the field, and this is for spruce. And if the buildup index is above a certain level and another of the fire indices, the fine fuel moisture code, has a certain threshold, the firefighter can determine, is this extreme or low fire danger. And the fire indices are fairly straightforward to calculate, except they do need early afternoon values of 2-meter temperature, relative humidity, 10-meter winds, and daily total precipitation. And so our goal is to, in the end, come up with something in the forecast product that would be usable by the fire managers. Let me step back here. In Alaska, we're challenged in many ways. We're challenged with ground truth. So, one of our sets of gridded observations that we're using are taking the ERA interim reanalysis and downscaling it to 20 kilometers using WRF. And this provides a better resolution for mesoscale features, and the downscaled temperature and precipitation are more realistic than when we use the coarser scale. We're able to capture the topographic effects. And this provides us with hourly data. So I'll show some results from quote-unquote observations first. This is a time series that shows the number of days that BUI is above a certain threshold from the reanalysis data. And for the period 79 to 2015, we see that 2004 and 2015 over interior Alaska had fairly high BUI, which is consistent with how many observed acres were burnt. But we also see that 2013 was a hot and dry year, and it had a high BUI, but it was not a high fire year because it had very few ignitions, so there was very few fires. So BUI isn't the full story. We need to capture some sort of prediction of ignition as well as weather. And we are trying to use seasonal forecasts in order to provide some of that information. So our study data that we're using is the North American Multi-Model Ensemble, which is an operational seasonal forecast that comes out every month. It's made up of 8 models that are available, and right now the work that we're doing end-to-end with CFS first, and then we're going to apply everything to the other models. And for the observations, as I said, we're using dynamically downscaled ERA interim. We're going to calculate the Canadian forest fire weather indices, and I'm just going to focus on the BUI, the buildup index. And then at the end, I'm going to talk a little bit about work done on taking observations of lightning data and seeing how much predictability we have of lightning possibility. I'm not quite sure what to call it, lightning risk. So we look at the plot on the left shows observations from, quote unquote, observations from the downscaled reanalysis of July 2-meter temperature. On the right, we are looking at the forecast of March, a forecast that starts in March of July temperatures. And the large-scale features are captured in the long-term climatology of the CFS forecast, but some of the details are not there because of the resolution, but which one wouldn't expect to get. Similarly, for precipitation, the observations are on the left. We see blue, where we're getting higher precipitation associated with topography. And on the right, some of that is captured. We see the Alaska Range and the Brooks Range. And we see some of the lower valleys, the lower precipitation values. So climatologically, things are reasonable for the July forecast. We step back and look at the CFS correlation scale map, and I've put arrows where we're pointing to Alaska. This is the March forecast, March start forecast, and it's a 3-month correlation of June, July, August, temperature on the left and precipitation on the right. Temperature provides some scale between 0.3 and 0.5 correlation, 0.2 and 0.5 correlation. Precip has less scale, or no scale in the seasonal, but in the July forecast, there's highest scale for both temperature and precipitation, so July does a little bit better. So again, we're starting with skill that may not be exactly where we want it to be, but let's see what we're getting. Now, if we look at climatology of the buildup index for July, left is the observations based on the downscaled reanalysis, and right is the March forecast for March initialized forecast for July. The general pattern of high and low values correspond reasonably well in the upper Yukon Valley, though some of the details are not captured at the 100-kilometer resolution in the forecast. So next, we're going to look at, this is the CFS forecast of the buildup index for interior Alaska. And this shows all the different years that are available in the hindcast of the CFS and North American Multi-Model Ensemble. And the dashed line shows the multi-year average, and I'm showing the buildup index from April until October. And it's a value that is accumulated. It reaches a peak in the middle of the summer when the chance of fire is the highest. The fuels are drier just before the rain starts. And some of the features that are captured are that in the 2004 fire, we see that the values of BUI are a little bit higher than average later in the season. In the 2015 fire, the red line shows higher values early in the season, which matches up with how the acres were burnt. The 2013 shows higher values all throughout the season, the hot, dry year, which didn't have ignition. And 2017, which is the forecast we were preparing last year, showed slightly above normal from the forecast, but we didn't have, we had a very low fire year. Now, this is a plot we showed to the fire managers in March of 2017. It was the buildup index average for all the ensembles, 35 ensemble average. And first of all, I think it wasn't, the managers didn't respond very well to this plot. It was not, and that was part of us gaining experience on how to communicate this. Also, the values were very small compared to what is based on observations. We're around 12 here, so everything's scaled down, partially because fire managers use data from point sources versus a gridded average, so it's going to be smaller. But overall, the values, the means are smaller. And how do you communicate ensembles to the fire managers? So we've gotten a bit better at that, but again, these are one of the challenges that come along in this project. So one of the things that became clear is we need to create products on the right spatial scale. So now we are doing all of our analysis on these predictive service areas to divide up our domain. And there you can see all the different colors. And observational data is available for each of these predictive service areas that the fire managers use to calculate buildup index and the different fire indices. There's also last day of snow and a variety of other variables. So now all of our analysis is focused on using the predictive service areas, except instead of, say, a larger area that we're used to using, like climate divisions or for interior Alaska. So now this is showing one of the predictive service areas, the upper Yukon Valley, and this is the buildup index, goes for 2015, that spans from April until September. The black line shows the buildup index based on the station data average for the upper Yukon Valley. And there's a different scale on the right-hand side for the forecast in blue from CFS, and then the downscaled observations. So one of the things, besides the magnitude being smaller, we see that in the early part of the season, the BUI is much too low in the forecast. And if we, as we explore that further, we find that doing some sensitivity tests and evaluating just the biases in temperature and precipitation, we find that precipitation is too high in the spring and the temperature is too low, consistently throughout all of interior Alaska. And here's the buildup index for the Tanana Valley West PSA, which is where Fairbanks is located. And the black line shows the observed buildup index, again, for 2015. The blue line is the forecast. So, and again, the forecast is a multi-model ensemble. So it's not quite fair to compare a multi-model ensemble to a single time series. So there's some of that going on, but it's comparing apples and oranges. If we use observed temperature and forecast precipitation, we get the green line. But if we use observed precipitation and forecast temperature, we get the pink line. So we see that certainly for the later part of the season, the precipitation plays a more important role in getting us closer to observed BUI. So again, through this process, it became very clear we need to come up with corrections. So right now we're developing corrections for using each PSA and using the station data as the true observations, and we're applying quantile mapping to determine these corrections. And again, there's challenges associated with that. And we're only going to correct temperature and precipitation from the forecast. The other variables are a bit more difficult to correct. Quantile mapping is a method that's been used pretty extensively, and this shows the cumulative distribution function, which tells you the likelihood of having a value less than a certain number. It's the integral, the area integrated under a PDF. And if we have a certain map model quantile and a certain observed quantile, we're basically moving them closer together. So you're changing the amounts that you're correcting depending on where you fall on this. And right now we're in the process of doing these corrections using PSA station-based data from 94 to 2010. And, you know, again, there's some challenges with this. The data needs to be treated sensitively in order to, you know, get the most out of the correction. So I don't have any clear results to show at the moment for that. Now, the other piece that we've been looking at is the lightning, and lightning data is available throughout Alaska, and this is the time series on the right of the historical and the more recent. The sensors were changed in 2012, and some of this trend has been attributed to a change in the number of sensors, and Peter Bieniek has been leading this work, and he's done some homogenization of the data between the two sensors, and it's a fairly simple homogenization, and he's gridded it to the ERA interim 20-kilometer grid just so we can compare it to reanalysis data to develop relationships between the number of lightning strikes and the various meteorological variables. And I'll show just so the thing that Peter's done looks promising is he's developed this multivariate regression between observed lightning strikes and different downscaled ERA interim parameters. He's used convective precipitation, vertical temperature gradient, which is a measure of stability, dew point temperature, 2-meter temperature, and 500 hectopascal height. And this plot on the left shows correlations, skill correlations, from the period late May to mid-June, where the predictions seem to do pretty well. At least there's a correlative skill. It's larger over certain parts of Alaska. It's lower over the southern part. And the next step that Peter's doing is he's going to apply these now to the forecast. So again, some of the work that needs to be done is developing clear relationships between fire danger in Alaska and the large-scale climate. There's some of that work's been done, but there's still more to be done. And that will help us work with the forecast better. Kind of the way forward is to develop seasonal guidance using the corrected BUI and the lightning strike. Kind of both of those pieces need to be put together to develop a more robust seasonal forecast for the fire managers. I think identifying the biases in the various models will help us contribute towards model improvement. You know, in general, there's quite a few biases at higher latitudes just because in the modeling centers that, you know, work is just really intensifying in that part of the world. Understanding the model skill will help us communicate to the forecast managers, and you know, it's sometimes slow going with a multidisciplinary team, but I think that's really the only way we can co-produce useful products, and hopefully, you know, in a year we'll have some nice picture that we can show that will be useful. Thank you.
Hey, Uma, that's great. Thank you so much. Let's see, we can open it up for questions. On the line, if you have a question, you can use the chat feature. Let me know you have a question. I see there's one already, actually. So this individual is asking if you think that the BUI data from the CFSV2 model is available for the Caribbean region. I assume that they would just have to do the same calculations, I guess, with the output.
Exactly, yeah. The data is available to do the calculation. We only calculated it for the higher latitude, so we didn't calculate it globally. But, you know, email me and we will share our codes with you so you can run it. So we're happy to do that.
Oh, that would be great. So to the question asker, that was Glenroy Brown. Glenroy, please, you know, get in touch with Uma about that. But yeah, the CFSV2 data is, you know, freely available and archived, and you know, you can get the data and then utilize those routines from Uma that she's willing to share. So thanks, Uma. That's great. And let's see, there's another question. Let me get this up on the screen from Jim. So Jim was asking whether you've considered skipping the middleman of NMME and CFS and instead using March SSTs and snowpack with a statistical model. And then, you know, he says that just points out that sometimes the models have difficulty with the teleconnections. CFS predictions of July SSTs might be valuable as well.
So as part of other projects, that work is going on. So there are other folks working on that. And some of that I've been a participant to. But yes, I totally agree that understanding that climate dynamics is really important because that helps us evaluate the models. One thing I didn't mention was that and I'm not going to remember there's a Canadian group that's actually done some really nice work of using analog forecasts in conjunction with their 2-week forecast to improve the skill. So again, understanding those analogs requires a better understanding of the climate dynamics.
Yeah.
Yeah, that's very important.
That's great. All right, Uma, thank you. I think we have to move along in the interest of time, but that was really great to hear about your project. So thank you for the presentation. Okay, and the next speaker is Jim Randerson. Jim, are you on the line?
Yes.
Okay, great. So I'm transferring control over to your computer right now. And
okay.
If you, oh, perfect.
All right. Did that same thing, didn't it? Let's see.
Yeah.
Let's flip it. Okay.
I think it's the swap presenter, yeah. Perfect. Looks good. So whenever you're ready, go ahead. Thank you.
Okay, sure. So I'd like to speak briefly about prediction of fires on decadal, seasonal, and daily timescales. And so I'd like to start on the second slide with describing trends in fire. So I'm a part of a group called the Global Fire Emissions Database Team, and we've been working to use satellite data from NASA and NOAA to map out fires over the last couple of decades. And so we're in our fourth version. It's called GFED4, and the top panel shows the mean global pattern of burned area derived primarily from MODIS data and using some other satellites to push it back to 1997. And the bottom panel, this is something that maybe not everybody fully appreciates, so I thought I'd show it here to provide context, is that we're losing fires from the Earth system. There are a few places, if you look like up in northern Canada, where you see an increase in fires, or in the Brazilian Cerrado, the red, some places in South Africa and in Southeast Asia and China, there's some red zones. But if you look across the globe as a whole, on the bottom panel, there's a lot more blue than red. And so that is the linear trend over this 19-year period at each grid cell. It's the slope of the regression. And so you can see that fires have declined by more than 30% in North Africa, behind the deforestation frontier in South America, throughout Central America, and across the Eurasian steppe from the old Silk Road going from China to Europe. And there is a downward trend in Australia, but there's a lot of climate variability there as well with El Nino. So this was a surprise to us in the context that the planet has warmed over the last couple of decades. And so we tried to understand this better. And so the next slide shows that we thought, well, is this possibly a change in climate? We tried to build a statistical model at each grid cell at a quarter degree to take into account the effects of rainfall. And so we tried to remove the effects statistically of rainfall. And when you do that, the original trend is shown in the orange or kind of red-brown line. And when you remove the effects of precipitation, the variability in the global trend in burned area declines a lot, but the overall trend from here it's using the higher quality MODIS data when we had 2 MODIS satellites from 2003 to 2015, because we were also looking at fire sizes and fire number. But you see that the trend is basically the same. So we don't think it's really related to climate, this loss of fire, nearly 25% decline in burned area in the Earth system. And what it is instead really is it's the loss of ancient grasslands and fire suppression driven by expansion of agricultural activities across many of our savanna and grassland ecosystems. And this, I mean, it really, in a sense, it did happen in the Midwest and the U.S. as well. If you went back, I think Ed would have this critical zone in the Midwest, but now we have so many agricultural areas across the upper Midwest that fires really can't expand. And so this is just an example of an actively burning fire from Landsat 8 that was collected by Doug Morton. And you can see the tongue of the savanna that's intact, and you can see fires burning up to the edge, and then you have these, it's basically an island surrounded by expanding agriculture. And so if you look at it then in the next slide, this is the spatial correlation. In each grid here is 1.5 degrees, and it's looking at the spatial correlation of 36 quarter degrees in that area. And so between population density from Landscan, from the Department of Energy, and mean burned area. And so where it's negative, it means that spatially, places where the populations are higher, and this data is at a very fine resolution. The less than 0.05 degrees, extremely high resolution population data. So you see that in tropical forests where you have more roads and more people, you get more burning. But you see in these grassland areas, if you look, I guess you can see my cursor as well, is that right? So you can see where more people, and we've also done this analysis for livestock and for agricultural area, you get a negative correlation again across this Eurasian steppe, behind the deforestation frontier in South America, and in both sides of the Congo in Africa. So, so it's this expansion. We've had a lot of great achievements in the last decade in reducing deforestation, for example, in the Brazilian Amazon, but there's been a massive agricultural transformation of much of the planet. And the other thing I draw your attention to is that you really don't see a large control in the western U.S. or in boreal ecosystems, where Uma was talking about here in North America, but check out, compare it with Eurasia. There's a much, we think this is actually a much stronger footprint of humans on ignition in Eurasian temperate and boreal ecosystems, especially boreal like large forests, compared to what you see in Canada and Alaska, where we just heard that lightning is a really critical driver. So we wouldn't expect this population control as much on burned area. So from a decadal perspective, this loss of fire, it's been very difficult. I think you heard last Thursday from Sam about this, and I just wanted to show this plot. So it is really, there's a whole class of models that try to predict decadal changes in fires because it's such a critical forcing of the Earth system from an aerosol and carbon cycle perspective. And so what's shown on the left panel are these observations from the NASA and NOAA data. That's shown in the black. And then the predictions from different state-of-the-art global dynamic vegetation models. And then the right panel shows the mean global burned area predicted by the models on the x-axis versus the global, the relative trend. And what you generally see is that none of the global dynamic vegetation models can really predict the magnitude of the decline. And part of it, I believe, is because it's really challenging, and the models haven't taken the steps fully to integrate the effects of people on the landscape, including the expansion of livestock and fragmentation from roads, and the placement of orchards that might serve as fire breaks globally in these grasslands. And there's also, you can see that some of the fire models have a difficult time predicting the total amount of burned area as well. So the observations are here, and most models predict too low a total amount of global burned area, and their trends they underestimate the trends significantly. So moving forward, if we're trying to project longer-term trends, trying to get a better representation of human land use effects, I think, are going to be critical. But it's kind of it's a little scary or interesting that you know, many of the animals in these ancient grasslands, they depend on fire, as we know, to maintain their grasslands and not allow for woody encroachment. And what we're seeing really is a global transformation of this biome globally. And I can just go back really quickly just to highlight, you know, this doesn't mean that fires are, if you look at forest fires, most of the place where we have a loss of fire, it's in the grassland systems globally and where you have fragmentation. But we do see an increase still in forests of fire. So it's still a really important problem, and climate is, of course, a really important challenge for western wildfires in the U.S. It's just that this global perspective, we're having such a big effect, the human footprint, through our expanding industrial agricultural programs. Okay, so then now I'd like to turn to the interannual timescale and the role of El Nino, and this was some work with Yang Chen, led here at Irvine with Neil Zandella and Doug Morton at NASA and Louis Giglio. And this is looking at burned area, and here this is burned area, and it's the correlation between El Nino 3.4 with a burned area at each location with a 3-month lead time. So it's just basically going from the SSTs, and we're using here the NOAA OISST time series to predict the distribution of fire. So you see that El Nino has a really large effect throughout South America, Central America, parts of boreal North America, of course, in equatorial Asia, and a very strong negative effect in Australia that I'll talk about. So where you have darker blues and darker reds, this is where El Nino holds some potential. And if you combine Nino 3.4 was the dominant one, but if you combine information on the SST state of the tropical North Atlantic and the Indian Ocean, you can actually statistically predict with a 3-month lead time a significant amount of global fire variability. And this paper was published in ERL in 2016, and now we're trying to extend it really for emissions to help with the global carbon project's estimates of changes in the global carbon budget from one year to the next. So here's so then this is a more recent paper in Nature Climate Change that shows a composite of El Nino. So we took the El Ninos that are shown here in the red, and we're building a seasonal composite. And El Nino, of course, is phase locked to the seasonal cycle, so it tends to peak in November, December, and January. And then we also have a series of years defined according to NOAA on which ones are El Nino, La Nina, and neutral from the El Nino webpage. And then if you look at this, though, during an El Nino, when we know an El Nino is starting and building, and there's a very strong element of predictability on the growing El Nino, it leads to a predictable fire cascade. So this is now using the GFED record to look at emissions. And so what you first see as you move into an El Nino from that first July and into the second year, you see first Indonesia lights up, and there's a huge amount of emissions as the Walker circulation shifts to the east. And so you have drying across equatorial Asia. Then you have other fires across Central and South, especially Central America, and some emissions from Southeast Asia in here. And then finally in year 2, even though the El Nino is gone, you've got biosphere-atmosphere coupling through the moisture and the soil moisture that leads to a drought and less evapotranspiration in the Amazon. And you get a pulse of fire kicking out in year 2. Even though we're back to neutral conditions, you still have a fire pulse because soil moisture was set back here during the wet season in the Amazon, and the reduction in soil moisture provides less water for transpiration by the trees, and as a consequence, the surface humidity dries out in response to the soil moisture deficit, and you get fires growing larger more quickly through the understory and through areas. So here's the burned area picture. You get a negative effect in Australia. So here's the potential. You have your observed SSTs. This is the predictability that we explored in this paper. For equatorial Asia, you have a high degree of predictability, a relatively short lead time from when you have this onset of El Nino. Here's the spring barrier to predictability, so you might be able to extend your forecast for fire by using what Uma is showing, like for the CFS or the NNME. So we're excited to continue to explore that at a global scale. And I just want to point out Australia is really remarkable. So when you start moving into an El Nino, there's less fuel buildup because it's drier in northern Australia. And so you get actually a suppression of fires in these systems that are fuel limited. And you get predictability that extends out more than a full year once you know you're entering into an El Nino. So some of the Australians, we see sometimes this paper is actually covered by an Australian magazine, I think, in part because of this really long lead time with El Nino. And then here's this paper is really describing this cascade across the tropics. So this is, again, a composite of different El Nino and La Nina events. And here's the fire emissions, burned area. You see it light up in equatorial Asia first. Then it moves to, the fires move to Northern Hemisphere, South America, Southeast Asia, and Central America during winter. And then finally, you get a positive pulse in the Amazon, Southern Hemisphere, South America, and a negative pulse in Australia. And that's, if you then use all the available satellite imagery that we have to track this cascade of fires across the global tropical land surface, you can see it showing up in optical depth. You see that same kind of cascade across different continents, and you can see it in the carbon monoxide columns from Moppet, and then also in rainfall to a lesser degree and in terrestrial water storage from Grace. So the last thing I wanted to briefly speak about was this emissions prediction on a daily time scale. And so I'm working with Porrick Smith and Casey Graff and Shane Caulfield on trying to build a predictive system for NOAA and for NASA's smoke forecasting system. It's my understanding that many of these systems now predict smoke, or the active fires on day. Well, there's, I guess, two components of the active fire prediction that we're looking at. One is new ignitions and one is existing fires. And so, you know, emissions from new ignitions are likely to be dominant on savanna and agricultural systems. From existing fires, these are likely to be a dominant term for smoke production in western and boreal North American systems. And our goal here is to try to say, right now some of the smoke forecasting systems use active fires and they use persistence. So they predict that over the duration of the weather forecast and the smoke transport, that the fires that we observe on the current day are the same that we project out into the future. And so we're looking at using machine learning techniques to try to better predict the active fire distribution so that they could be used, you know, if we have a weather storm or a rainfall event that comes through or the winds pick up, could you actually predict an increase in the active fires and provide that to the smoke forecasting system? So what we do is we cluster the active fires together to try to put, right now they come back from the satellite, it's just you get a lat-long coordinate of where the active fire is. We're clustering them together, and then we're extracting climate information at each cluster from from NOAA's weather forecasting system. And so we then take the weather forecast, so this is like a weekly weather forecast, and we predict the evolution of that cluster. And so, of course, there are a really extensive set of sophisticated models that predict fire growth, but the challenge here is to be able to do this at a regional or global scale simultaneously in a simple way. So here's an example of a cluster that's growing, and we're using the global forecasting system. Right now we're using the analysis product, but we're also going to use the archived forecasting products to try to predict how these clusters grow to give a better estimate of the active fire distribution over a period of 1 to 5 or 7 days into the future to provide to a transport model like NOAA's transport system or the NASA one for their forward processing system. Okay, and so here's what we've been able to do. So the baseline is the predictive model where it's just persistence. So this is the mean absolute error, and we're focusing in on Alaska to start with for this problem because that's a really nice place where there are really great fire records, and it's dominated by existing fires. There aren't that many new ignitions compared to these larger fires often dominate the total amount of emissions. So we're doing the existing fire component of the problem first. But so the baseline is just persistence, and then if you go to auto regression, you can do a little better. And then if you use the GFS information on temperature and humidity, you can reduce your absolute error on forecasting the total number of active fires up to 5 days into the future. And then much of the information is actually coming from temperature. And then I think the second most important variable is humidity, and you get a little bit more. We're still trying to, I think we do want to switch to a system where we're using the Canadian fire weather system, but right now we're just building into the machine learning just directly the variables of temperature, humidity, and we also have a cumulative rainfall variable that in a sense is simulating things like the BUI. Yeah, so that's mostly, just wanted to touch on those 3 different timescales that I'm really interested in thinking about fire prediction. So thank you.
Great, Jim. That was a really nice look at all the different kind of work you all are up to, so thank you for that. If there are questions online, please send them in. Any questions in the room for Jim?
Yeah, Jim, this is Anarita. Very nice talk. I was wondering, you looked at the connections between burn area and the predictability of burn area and El Nino. I wonder if you have explored the connections with Madden-Julian oscillation, MJO, on short time scales.
No, that would be really neat. I mean, that seems where you have a lot of potential, right, for that S2S timescale with the propagation of that through Asia. And it's a great idea. I mean, yeah, we should talk more about it. I mean, that would be, it'd be neat. I mean, especially now with VIRS, the instrument where you're getting more active fires. So you have to be able to resolve. Before with MODIS, you had like a 1.5-day repeat time in the tropics of equatorial Asia. That's where, of course, you'd probably start. But now with getting more coverage with VIRS as well, I think you might actually be able to see, I guess, something like weekly to 10-day waves moving through, but I'm not aware of anyone who's done it. Maybe someone else can comment who's online, or I think it's a really good question.
I don't know if Uma or Ed have a comment on that.
Yeah, people, just to comment on that, just one more aspect that's kind of funny is that people have seen that, like during big soccer events, you can see the fires turning off, or in Africa, for example, in Muslim-dominated countries, you can see less burning on Saturday, and in countries that have more of a Christian faith, you can see less burning on Sunday. So you can see these weekly oscillations in the number of active fires that are set by cultural and religious, I guess, preferences, and I think that. So I think there would be potential for looking at these, the Madden-Julian oscillation.
Thank you, Jim.
Jim, I guess I was wondering, on the slide you mentioned Sam Rabin had shown something similar last week.
Yeah.
So showing the inter-model comparison and also the baseline with the observations. It seemed like there was one model from Lund University or Lund University maybe. There's like a brown line that seems to have a really high correlation with the observations. On the left-hand plot, I guess, yes, the right as well. Is there some, what is it about that particular model that seems to capture the variability and the trends so well?
I'm not sure that model. So that was, I think that was Stein Hansen, and the Blaze, and it's a simpler model than some of the Spitfire ones. But I agree, that's the one that holds the best promise. There were a couple different, that evolved. And so whenever you have a process like this, the data are evolving and then the models have a target. And so I know we had to at some point finalize the models for their comparison with these data. But you're right, I think that is my sense as well. That's the best model. And it is simpler, it is prognostic, it does include things like it does have pastures in there and some land use change. But I kind of feel that at this point, having a simpler representation of these different fire processes may provide more predictive power. If you have a smaller number of parameters that you can optimize, that may be more valuable than really trying to make a super mechanistic model that it leads to more complexity, and sometimes it's more difficult to capture these things like the interannual variability. But this is, I think, Dan, this is the first time that most of the fire models really were predicting off the mean annual burned area and the seasonal dynamics. And so now we're finally getting decadal scale records. There's a greater appreciation of the importance of these changing and expanding populations and how important that is for setting fire regimes.
That's interesting. Thanks. Yeah, sometimes the complexity degrades the performance. Okay, well, I think we need to move on to the next speaker, but again, Jim, that was really great. Thanks for the really nice overview of your group's work.
You're welcome.
So final speaker is Adam Kochanski from the University of Utah. Adam, are you on the line?
Yes, I am.
Great. I just transferred control over to your computer.
Welcome, everybody. This is Adam Kochanski, and I would like to talk today about recent advancements in smoke modeling using coupled fire atmosphere model work with fire. So we will go to a little bit smaller scales, and we will be talking more about high-resolution modeling with explicit treatment of the fires and the fire propagation. So as a motivation of the study and what we did recently is that it has been recognized that the aerosols emitted by wildland fires impact large-scale weather and climate, and because of that, accounting for fire smoke allows to reduce errors in medium-range weather forecast. And that's something that Francesca talked about, last week, during the previous webinar. So here we ask a little bit, different question, which is basically if those effects are also important in the context of short-time local weather forecasting. And in particular, if the local inversions observed during the fire seasons are really associated with smoke, and how the fires and the smoke can impact local temperatures, and at the end, if we can use, coupled fire atmosphere models to simulate, these effects. So let me start just from a brief explanation of what WRF as fire and what as fire can modeling framework do. So basically, the system is built around weather research and forecasting models. So that's the main core of the system, and it's coupled also with chemistry. So you can think about it as a WRF chem. On the top of that, what we have is Aspire, and Aspire basically has three main modules. So there is a fire spread model, and the fire spread model takes winds from the weather model and computes fire progression through the landscape. It computes also the release of heat and moisture, and basically feeds those fluxes to the atmospheric model, so the atmosphere is affected by the fire itself. Now, the other way how these two systems are linked together is through the fuel moisture. We have air temperature, relative humidity, and precipitation, and that goes from our atmospheric model from WRF to the fuel moisture model. So the fuel moisture model basically computes that fuel moisture in different fuel moisture classes, and that information is also used then in our fire spread model. So depending on what is the amount of moisture in the dead fuel, depending on that, the fire will propagate faster or slower. Once we know how fast the fire progresses and through what type of fuel, we can compute the fuel consumption, and based on the fuel consumption, we can then compute our emissions. And those emissions may be either like a simple passive tracer that can be then just handled directly by the WRF dynamical core, or it may be just a mixture of chemical species that are then fed into the WRF chem. So the chemistry basically can respond to those fluxes and compute all the chemical transitions and the transport. So there is a couple of unique features of this system. So the first one is that it utilizes multi-scale coupled fire atmosphere model. So it means that you basically can set up your simulations in those multi-domain configuration and have those coarse scales resolved by outer domains, and then you can scale down to high resolutions needed to resolve your local weather or the small scale impacts of the fire itself on local weather conditions. In this system, the emissions are computed in line with fire progression. So basically, the growth of the fire is modeled on the model grid, and based on the progression of the fire itself, we compute heat release and all the emissions and so forth. Because this system also is integrated with the fuel moisture model, basically the fire progression also is impacted by the local weather conditions at different time scales. So by having this connection between the atmospheric model and the fuel moisture model, we don't really need to make any assumptions in terms of diurnal variability of the fire itself, because it is going to be just the consequence of changing weather conditions. And if we are going to have strong diurnal variation in terms of relative humidity, we'll also have, as a consequence of that, changes in the fire behavior. This system also allows to assimilate dead fuel moisture observations from surface weather stations. So there is a way to actually initialize the model and provide the initial guesses of the fuel moisture in the sense of just spatial maps that then a model can modify once we perform our simulations forward in time. And as a new addition that we just added to the system, it also accounts for radiative impacts of smoke. And that's something that I would like to really discuss during this presentation. So here I'm just showing the configuration that we used to simulate the effect of smoke from 2015 California fires. And here we are using 3 nested domains. So I mean, you realize that we are going here to much higher resolutions than all the global approaches. And also as a consequence of the fact that we simulate the progression of all of those fires, we basically don't use any assumptions in terms of fire persistence. We actually just try to model as as good as we can what the fire is gonna do depending on the weather and fuel moisture conditions, and that's what actually drives the emissions. So we have here 3 nested domains, and we simulated 5 fires in our innermost domain 3. That's at 1.3 kilometer resolution, and you can see here the fires that we simulate. And also we have one additional fire which is in domain DO2, which was added just because it contributed to the smoke within our innermost domain. Now, in terms of the fire progression itself, we actually constrain, in this case, our fire progression based on observed fire perimeters. So we process fire perimeters and generate fire arrival time, which is then used to steer the fire progression and our fire spread model. And here we perform 2 simulations. We perform one simulation which is with no radiative smoke impacts. So that's just pure WRF as fire. And the other one is WRF as fire with CAM. And in this configuration, we also link emissions in terms of PM2.5, PM10, organic carbon and black carbon through the go-kart scheme. And for this particular study, we used emission factors derived from Urbański, 2011, and Akagi. And as I mentioned, the fire progression was here estimated based on the analysis of fire perimeters. So here is just an animation showing what the system does. So those red spots, those are the actual fires that we model. So each of these fires grow, it consumes fuel, releases moisture, releases heat, and also releases fluxes of organic carbon, black carbon, PM2.5, and PM10. And you see that this coupling between the atmospheric model and the fire model gives you a really highly variable smoke field, and that's something which we would like to see. And also you can even see some small features like smoke which is trapped in local valleys, and that's something that I will be talking about later on as well. So here is a map showing elevation in our domain DO3. That's our innermost domain where we have most of the fires, and the location of 2 weather stations. One is the Big Bar station, and one is the Trinity Camp station. And those are the 2 stations that we are using to compare our simulated solar radiation, also temperatures. And there are 2 differences between them, and then the reason why we picked these 2 stations is one of them, the Big Bar, is a station which is located really deep in the valley. So it's covered by a really thick layer of smoke. And the other one, the Trinity Camp, that's a station which is a little bit higher up, so it's covered by a much shallower layer of smoke. So we expect to see differences in terms of the impact of smoke between these 2 stations. But before we go into that, I just wanted to show the analysis of the plume top heights. And on the left side, you see for the August 18th, that's the Miser plot showing the plume top heights derived from the satellite. And on the right side, for the same time, it's our simulated plume top height using a worthless fire with CAM. And we are pretty happy with the results. They are very close one to the other. We have plume top heights between 3,000 meters and 3,500 meters. So that's like a sanity check that we had to perform just to make sure that we represent the vertical structure of the smoke correctly. So having that, we started looking at the thermal effects and the effects of the smoke from the fires on the solar radiation. So here I'm showing two plots for these two stations that I showed you on the map. So the first one is the big bar station. That's the station which is really deep in the valley. And the one below, that's the Trinity Temp station, which is a little bit higher up. And there are three lines here. So the black line, that's a line just reconstructed based on observations. So those are observations from this RAS weather station, and we are looking just at the solar radiation from the station. The red line, that's our pure regular worthless fire simulation in which we don't take into account any radiative impacts of the smoke. And the orange one, that's the simulation in which we use worthless fire coupled with the go-kart scheme through the WorthCam. And you see right away, especially on the August 20th, that there is a really significant reduction in incoming solar radiation. And there is a really big difference in terms of what the model shows if you neglect the smoke impact or if you take that into account. And here we are talking about differences up to 400 watts per meter square. If we look at the bottom plot, that's the plot for the Trinity camp, we have a little bit smaller impact of the smoke on the solar radiation, but in general, by taking into account the smoke and how the smoke reduces incoming solar radiation, we really can bring our simulations and our estimates of the solar forcing. We can bring it much closer to reality. So that's what the smoke does in terms of the incoming solar radiation. So you can expect that because of that, we would also see some differences in terms of the surface temperatures. And that's right, that's correct. And here on those four plots, I'm showing the impact of smoke on 2 meter A temperature. So basically, those are differences between the simulation in which we have fire, but we don't take into account relative impacts of smoke versus the one where we include that. So basically, by having this interaction between the smoke and the radiation scheme, we can reproduce and we can see surface cooling here reaching up to 3 degrees Celsius. So that's really important thing. And also, if you look at these maps, you see that the pattern of those of the temperature and those places and the regions associated with really strong cooling, they have very complex pattern, and this complex pattern actually is controlled at least to some degree by topography. And here I'm showing on the left side that the Miser visible image showing you the smoke, and on the right side there is again our map showing elevation, and the bottom one showing the temperature difference. So you see that actually those regions where we observe very, very strong surface cooling because of the smoke, they correspond to those deep valleys that basically can hold a lot of smoke, and this deep layer of smoke may have a strong radiative impact. And if you look at this Miser image on the left side, you can actually see that those canyons that you see on the map on the right side, I mean, they are actually visible on this satellite image, and those are the places where smoke is very, very thick. So another thing that we would like to a little bit understand more is what is in general terms thermal effect of smoke in terms of the vertical temperature structure. And here I'm showing a plot that shows the difference between the two simulations, taking into account and not taking into account the impact of smoke. And basically, you can see here that later in the daytime, there is really significant surface, near the surface, cooling. So that's, one element. But also, on the top of that, the upper layers, there is more absorption of the solar radiation. And because of that, we have also warming of the atmosphere aloft. So basically, these are two elements that really increase stability of the atmosphere. And by just, cooling at the surface, warming aloft, the atmosphere gets more stable, and it's much, more, difficult to actually mix out the smoke, within the valleys. So from that standpoint, we have feedback between the smoke and the ability to actually get rid of the smoke and to ventilate the smoke out of the valleys. We have enhanced stability, and that basically inhibits any ventilation within those really deep smoked valleys. Now it's not the only impact because changes in the atmospheric stability, they also translate into the mixing. And this mixing then has an impact of the surface winds. So those are just 4 plots showing differences in the wind speed, and basically the impact of smoke here is reduction in the 10-meter winds by up to 3 meters per second. So that's pretty significant effect, which basically means that it's not just the issue of the temperature itself, but there is also another mechanism here that may inhibit mixing, which is basically by reduced surface wind speeds. So those are the effects of smoke, on the atmospheric conditions. And in general terms, if you think about it, it looks that the more smoke you get, the more stable atmosphere you can expect, and because of that, you will also have weaker winds, and it's going to be even more difficult to ventilate, the smoke. So that's a pretty important thing. So just to sum up, we here are just showing new capabilities that we added to work as fire. So that's coupling with the go-kart scheme, which now allows work as fire to account for radiative impacts of smoke. And we looked at simulated plume top heights, and it looks that for those 2015 August California fires, we have a really good agreement between the simulated and observed plume top heights. So we are really happy to see that. And it seems that the fire smoke really had significant impact of local weather conditions. And on the one hand, it caused up to 3 degrees of surface cooling because of blocking of the incoming solar radiation. It also caused upper layer warming, so stabilization of the atmosphere, plus also reduced surface winds. So all these elements basically strengthens local inversions and traps fire smoke in the valleys. And just the take-home message is, as we have more and more wildland fires and more regions are in smoky conditions, accounting for wildland fires becomes an important issue, and we believe that using coupled fire atmosphere models may help in resolving local impacts of wildland fires on weather conditions and also on air quality. So that's everything that I wanted to share with you today, and I'm ready for your questions.
Great, thanks a lot, Adam. That was a really interesting talk. If there are questions online for Adam, please use the chat feature or the Q&A feature. You can just let me know you have a question. I can unmute you. Any questions in the room?
Yeah, I have a question. Very nice talk, Adam. So I think you described how the smoke, introducing the smoke increases stability, in the atmosphere. However, I understand that some of the major fires, for example, those that we had in the western U.S. in 2017, can actually create like big chimneys and create this local circulation and this pyrocumulonimbus, where you can actually bring the smoke from the troposphere into the stratosphere and also have that travel, for example, to Europe from the U.S. Does this model capture this kind of dynamics that affects, both the smoke locally and also remotely, possibly?
Yes, I mean that of course depends on the resolution, and of course for really big fire events, you can in most cases go with relatively coarse resolution, and you still can account for the impact of this fire release heat and actually resolve pyroconvection and processes associated with that. So yes, it is possible, and we have some other cases showing that. This particular season and this period of time that we looked at, however, was slightly different because those fires that we simulated, they were not really that active. They were burning relatively slowly, but they were not super high intensity fires that could actually generate any significant pyroconvection. So it was more like stable progression. Fires were contained to a big degree, so they were slowly just progressing in time, but without anything very spectacular in terms of generation of strong updrafts or pyrocumulus clouds or and things like that. But the system itself, yes, I mean it is designed to actually account for that. So so in some other cases we actually see very strong updrafts, and we also see very strong modification of surface winds near the fire just because of the inflow of the air into those convective columns.
Great, thanks.
Great, thanks. There was one very brief question just about whether your temperature scale for the anomalies was Celsius. Somebody just wanted you to confirm that.
Yes, so those are all in Celsius anomalies.
Okay, pretty big anomalies. I don't see any other questions, so I just want to thank Adam for the presentation and taking the questions. I really appreciate you participating in the webinar. So that's the conclusion of this webinar and this 2-webinar mini-series on fire. I'm really grateful for these 4 speakers. I thought that they all were very interesting, a kind of diverse body of work, and between this webinar and last week's webinar, I've really seen an interesting cross-slice of a lot of the work that's going on in this area. And, this isn't representative of the larger amount of work in modeling fire and predicting fire regimes, but I think we got a really good sense of what's going on in the community. And today, I'm really grateful that Ed, Uma, Jim, and Adam, that you all took the time to present. Again, I know it was a lot to figure out a time that works for everyone, and we really appreciate you bearing with us and ultimately arriving at this time and participating in the webinar. We're very grateful, and for all the folks who attended as well, thank you, and thanks for all the great questions. We're going to post a copy of the slides and a copy of the recording on our website probably in the next couple of days, and you can go there to grab it. I'll just put the address up on the screen quickly. So it's cpo.noaa.gov/map/webinar, and you can go there and get the recording for this and last week's webinar, as well as all of our previous webinars for the last 6 or 7 years at this point. I don't know, I've lost track. 7. Anna Rita reminds me it's 7. Anyhow, thanks everyone for joining, and we'll talk to you later, and I really appreciate all the speakers taking the time again.
Thank you, Dan, for putting that together. It's really cool.
Absolutely. Nice to meet you, Jim.